if I were you, of course, I'm not, so it's irrelevant. You can do whatever you want. Myself, I would just leave, and you can watch the video, and you'll follow it just fine. So we were talking about. I'll remind you the definition of the tropical set. I actually gave a sort of stupid definition of it, so let me give it to it slightly differently. So let's say I have a variety U, and let's say I have a rational top degree form. Top degree. So it might have some poles. Form, say smooth variety, rational top degree form. This really shouldn't even, I mean, if you're an algebraic geometer, this isn't really, they shouldn't even think of this as the variety. I'm really just talking about the field of, the function field of this variety. But think of it as, if you like, if you prefer a variety. So I have UW, and let's talk about the tropical set of this. And what is this? So this is to remind you of, or this is slightly different than I phrased before, but it's the same thing. So it's pairs of a divisor and just an integer. So E is a divisor, an irreducible divisor where omega has a pole and m is a positive number. And I'll throw in 0, just an extra point I'm calling 0. And what's the meaning of this? What do I mean by a divisor? Well, this is a very kind of birational notion. So here I take U. I take any open set of U, Zariski always, Zariski open set V, and then I suppose that V is itself an open set in some other variety. If you're used to, I could just, all I'm doing here is basically avoiding the use of the field of fractions, or the field, field of meromorphic functions or rational functions. Just this is what it means. So I have U. Here I have this differential form, top degree form. Maybe it has some poles. I can restrict it to V. Maybe it still has some poles. Now V lives inside of Z, so it's also a rational differential form on Z. And then I just take E. So here's the picture. Here's Z. I've got some divisors on it, and here's one E, and that's what I could just ask. Does omega have a pole on E? So it's a pole somewhere. It's a divisor somewhere where the guy has a pole. Last time we rephrased this in terms of valuations. That's because you want to, you have to say you have to ask yourself, well, when does a divisor living on one variety, when is it identified with the divisor living on some other variety? Exactly if they give you the same valuation on the functions. Okay, but anyway, this is the definition. Now, in the case that we're considering, we have this kind of magical situation where, so if omega is a log form, that just means that there's never that if it ever has a pole, it's at worst simple poles. At worst simple. So you never get simple poles. So you never get a higher order pole. It just doesn't happen. That's what it is a log form. And Calabi Yau, we'll call say log Calabi Yau means essentially that there exists a unique up to scaling top degree log form, and it's actually a volume form. It's a volume form. So at the meaning that it's regular. There's no zeros or poles on U, or poles on U. Okay, you can take as the definition. It's not quite, last time I gave the precise definition, but that's what is log Calabi Yau. So now notice that if you have this situation, then that just immediate from this very definition, that if I have U and inside of it I have V, and let's say they're open, and let's say they're both log Calabi Yau, both log Calabi Yau, then necessarily the volume form for U must restrict to the volume form for V, just by the definition of uniqueness. And then if you look at this definition, their tropical sets will be just exact. Oh, sorry. And then in this case, we just write U trop is really U omega trop. So then their tropical sets are just equal. Tropical sets are just equal, just by definition, because it's defined up to this restriction thing. So the tropical sets are equal. And last time I indicated that if I took a torus, so for example, last time we said that if you had a torus, Tn, so this notation meant n tensored C star, where n is just a free abelian group, z to some, so this is C star to the n. The n are the co-characters of this torus. Tn trop was just canonically equal to just n. And there's also a real version for all guys. Here's an integer tropical set. here, maybe I didn't put that in the notation here. Yeah, this is tropical. This was the integer tropical points. There's a real version, so there's Tn. This is what Tn trop z is. It's n, and Tn trop r is just nr. You can define this with some, if you use valuations as real valuations. So the point is that there'll be loads of examples here. So in general, u trop r. In general, this is a piecewise linear object. Its dimension over r is less than or equal to the dimension over c of u, and you have equality if and only if, this is just the definition, if u has maximal boundary. So maximal boundary means that the tropical set is as big as it can be. For example, if you have any open set which is a torus. If you have an open set of your Calabi Yau which is a torus, then the tropical set is identified with the tropical set of the torus, which is just a vector space. Okay. If you say it again? Spherical variety? If you take an open some spherical variety. I am not sure. Let's discuss it after. Yeah, no problem. Let me just remark that in general, what's actually true is that this thing has, so when you have this max boundary, it's very surprising, the real tropical set, let's see, will it be helpful? I'll mention it. I didn't give you, though, maybe this is not satisfying because I didn't give you enough of a definition for you to appreciate this. Let me tell you what it is just in words. It's not going to be important in this talk, but it's the dual complex. How can you compute this thing in general? Let me just say quickly, how do you compute this thing? Suppose, so how do you can, I give you this weird definition. You can actually compute it pretty easily. Suppose YD is a simple normal crossing minimal model. Minimal model. So what does that mean again? What does that mean? It means that this is smooth, projective. D is simple normal crossings, and it's anti-canonical. Ky plus D is trivial. And then you can form this abstract dual fan. So then you form the abstract, so dual fan sigma YD. How many people know what this is? Can guess what this is? Or if you don't have any idea, or don't give any information if you don't prefer not to. But it's sort of like so this is, I think lots of you people have done something like this. So what's the dual fan? It's just the fan whose its cones are just in bijection with the strata of the simple normal crossing divisor. So let me just give an example. Let's say we're in dimension 2. Then this is what the picture always looks like. Say we're in dimension 2. This is a picture of YD. So Y is a surface. D is a bunch of curves. They're actually always P1s. They actually form a cycle. What's the abstract fan? Well, it's got a zero stratum. It's got a vertex that corresponds to the maximal stratum. So there's the 0 point that corresponds to Y. Each boundary divisor, each E, which is a codimension 1 stratum over here, corresponds to a ray over here, rho E. So I'll have a 1 ray for each of these guys, however many I have. And then I glue in a cone, a 2-dimensional cone for each codimension 2 stratum. So for each of these, I get a 2-dimensional cone. And you get an abstract kind of cone complex as the dual. It doesn't live in a vector space. It's just an abstract cone complex. And what's the fact is that the underlying set of this depends only on U. And this is exactly the real tropical set. And in this picture, it turned out to have really nice topology, it looks like R2. In fact, surprisingly, it does always. This is a theorem of, I think, it's due to Kolar. I think the meat of it comes from Shakurov, the theorem of Kolar, that this thing is always, in the maximal boundary case, this is always at least a Q homology Rn. Homology Rn. And I don't know an example where it isn't very close to being a manifold. Maybe it's always essentially like at worst like quotients of a manifold by a finite group. So this is a nice thing. So I think of it as, I always think of this as basically an n-dimensional manifold, and inside of it I have this discrete set of points. Okay? Now, if I choose a torus, inside of my U, which you can't always do, but in the examples we looked at last time, there's lots of interesting examples where you can choose a torus. Otherwise, there's another way of putting a linear structure on this thing. But if you do choose a torus, this identifies, again, we said this identifies U trop now with a vector space, with Rn. Or it gives an isomorphism of this with Rn, just Nr. But I want to just stress, this thing is not a vector space. This is not a linear thing. There's not a vector space. You can't add. There's no natural addition. Look at what it is. These are divisors with a thing. There's no way to add them. These are irreducible divisors. You can't, in terms of valuations, if you take two valuations and you add them, you get a function, but it's not a valuation anymore. It doesn't satisfy either of the two properties. So it's not natural to add these things. What this thing is, it's piecewise linear. So this is a piecewise linear manifold. So this is a piecewise linear. You don't know what it means canonically for a function on here to be linear, or you have to be clever to figure it out. What's natural is you know what it means for a function to be piecewise linear. And in all the applications I talked about last time, and basically what's always true is, what it'll have many different identifications with a linear object. There are ways to make this thing linear. You probably hear about integer affine manifolds, people in mirror symmetry. That's an artificial construction, that integer affine structure, but there's often infinitely many of those. So you can make, so it's basically it's a thing which comes with lots of identifications with a vector space. You can think of it as, or something a little bit more interesting than a vector space. All right. Anyway, that's the tropical set. I think that's all I want to say about it. I need to say at the moment. Yeah. Let me get to the main conjecture. So let's take YD. One of these minimal models. Minimal model. So just all this condition I just said, minimal model for U. Let's take. I have to tell you about the Mori cone in order to state the conjecture. So let's take inside of just the ordinary singular homology. Let's take. There's a certain nice monoid, a closed additive subset called the Mori cone, and this is just the set of. You take the class of every algebraic curve in Y, an algebraic curve, where I allow the curve to be reducible. Or otherwise, I don't allow it to be reducible, and I take the additive subset that they generate. But so the addition here is just the dumbest thing. What's the class? So here's a picture of Z, of Y. Here's a curve, C. Here's another curve, C2. How do I add them? Well, I just take the union with the right multiplicities. Or you could just say, take the classes of irreducible curves and then just take the additive subset they generate. So this is a monoid, meaning it's closed under addition.
Can I ask
Yeah.
a question more or less what he does? So if I take SL2C as U?
So SL2C is not a Calabi Yau. So it's but here I could take any variety and form this set. I could take any rational differential form. It is not Calabi Yau. No. No. Take a look at them. Watch the video. It's not. It has an open subset which is Calabi Yau. The A1 is not Calabi Yau in this point. It does not have a volume form of this sort. But honestly, take a look at the video. So here's the situation. So it's called the Mori cone, or it's the integer points of a cone. I'll call it the Mori cone here. So what am I going to do with this? Let's look at the associated ring. So let's take H2YZ, the group. The group. It doesn't satisfy my definition. This is the group ring. Inside of it, I take the subring generated by, call that R, by NEYZ. What is this thing? Just as a free abelian group, it's the direct sum over over each class of every curve of Z times a formal variable that I'll write as x to the c, where you just multiply in the dumbest way. X to the c1 times x to the c2 is x to the c1 plus c2. What's the geometric meaning of it? If I go to the spec of these two things, if I take the associated space, take spec of this ring, and here I have spec of R, this is the torus associated with the Picard group of Y. So pick Y tensor C star. So an algebraic torus, and this is a certain toric compactification. In fact, the toric variety given by a certain cone in the Picard group, the Neff cone of Y, which is, if you don't know what that is you take the ample cone and take its closure. You can, in absolute generality, this will be a pretty nasty thing. So let me make here, just for simplicity, let's assume, put a condition here, a positivity assumption, which also is natural. I'm going to be talking this at the moment. I'm talking all about functions on U, trying to find a basis of functions on U. If I don't assume that U is somehow close to affine, it won't have any functions. So I put that assumption in now. So one way to do it is, let's assume that D supports an ample divisor. Ample. For example, just assume that D is positive. Assume that Y is a Fano variety. That's the same thing as saying Y is Fano. This implies that U is now an affine variety, and it also implies that this is a nice cone, that this R is finitely generated. This is just a nice toric, the kind of thing you would take in toric geometry. It's just a nice rational polyhedral cone. All right, and now what's the conjecture? So now we take, so now I'm going to, let's just let A be the free R module. And by the way, if this R bothers you, this thing is you could just think of this as the constants. These are just the coefficients for my algebra. I've many times given this talk where I don't mention R at all. Just think of R as Z or C. You can ignore it. Let A be the free R module with basis the tropical set. And as I said in the first lecture, I'll just do this stupid notational thing. If I have P in here, I'll write theta P for the corresponding element of A, even though I should really just call it P, because that's the basis. So then A, just as a matter of definition, is the direct sum as an R module of P in the tropical set of R theta P. OK, now what's the conjecture? So the conjecture with Grosshack and Keel Siebert from about 11 is that this thing is naturally an algebra. So A is naturally, so first the main thing is, so A is naturally an R algebra. As I stressed last time, what does that mean? And when I say algebra, I mean finitely generated commutative associative algebra, R algebra. What does it mean to make this an R algebra? This is what this is equivalent to giving is, to give the algebra structure is equivalent to giving you the structure constants for multiplication. So what I really have to tell you is, if I take theta P1 times theta P2 and I expand it out in this ring, and I use the fact that R itself has this basis in terms of curve classes, that means I have to give you a direct sum over all elements, let's say R in this tropical set, and all curve classes of some number, which I'll call, that's the structure constant, P1, P2, R, C, that's just some integer, times this formal variable x to the c and the variable theta r. So to give it an algebra structure means giving you these structure constants, telling you, how do you multiply in this basis. These will in fact be certain positive integers. So the conjecture is there's a natural bunch of things to count to make this into an algebra. Let me tell you just very vaguely what it is we count. There's sort of two reasons. One, because it would take a while to make it precise, and really the real reason is we're sort of in the middle of what is the right way to count. The way we are with the theorems that we have currently, the count it's not so bad, but it could be a lot better. In Tony's talks, he showed what I think is a lot better, where it's a lot more concrete, so a lot more direct. So let me basically say, what are these counts? So what's the data that you have? You have P1, P2, R, and C. And what are these guys? These guys are, let's call this P3 just to make it symmetric. These are these this is a divisor at infinity, some divisor, and some multiplicity. And this is a curve class. So the picture I have is I'm giving you a bunch of, in some big compactification, I'm picking out a couple of boundary divisors. Like here's E1 with some number, maybe 2. And some other divisor, maybe E2 with some number 3. And then I've got this third guy, the third one. And I've got a curve class. And the things we count are rational curves. This is legit. We count rational curves that look like this. They touch this, but they only touch the boundary at 3 set theoretic points. They once is along this first boundary divisor with given multiplicity, once along here, and once somewhere else. Now, and we're C, and their class is C. This is as Tony mentioned in his talk. This is always a zero-dimensional moduli space. No virtual fundamental class. There's just a set of such things. You can just count them. Now, what I did not show you in the picture, I did not put down E3. That's because E3 is one of these boundary divisors, but that's not this guy, unfortunately, in general. It can't be if you think about it. The structure constants cannot be symmetric in the data. So what we're really counting, as Tony explained, we're really counting disks. And then it's asymmetric, where what the output here R is telling you about is where this guy is living on the SYZ fiber. But I really like this idea of Tony's to extend the thing straight, and then we count curves like this. It's really I think it's nice. Also, Gross and Siebert have what will work in all cases, description in algebraic geometry of how you count these disks. It's work in progress. Okay, but anyway, this is roughly what we're counting. The fun thing is for lots of the applications, you don't really need to know all the things I want to talk about. You don't need to know so much precisely what I'm counting. You just have to sort of know that it's some fun thing. That we have these positive structure constants. Okay, so that's the conjecture. First of all, is I can define these counts in such a way that I get an algebra. Then who cares? Let's say that's. Let's say now what's true. So 0. What's true afterwards? This algebra is the symplectic homology, the degree 0 symplectic homology. And we've been talking to Nick and James and hacking about trying to get these higher guys. Anyway, I have this algebra. So what can I do once I've got the algebra? Well, I can certainly take spec of A. No matter what A is, it's flat over R. So I can go to spec R. Remember, this was the toric variety. This was some nice thing, toric variety for the Neff cone of Y. This I'll just call V. Goes to here, and that's just equal. That's the definition. And inside of here, if you don't like this toric variety, we have this torus, just the torus for the Picard group of Y. Let's restrict. I'll just use the same notation for the restriction of the family. Just so we have this torus partially compactified. And what's the conjecture about this? The conjecture is that this is a family. So this is now a family of log Calabi Yaus, affine log Calabi Yaus of the same dimension as U. Same dimension as U. And notice what's good about them. Their algebra comes with a basis. Each let's say the family. Let's say the fiber is V, and of course OV comes with a basis. Comes with a basis BV, which is the tropical set of U. So what's nice about them is they're log Calabi Yaus, but they come with a basis of functions by the very construction. At the moment, this family appears, just from the data, to depend on the compactification of U that I chose. For example, that's the Picard group of Y. It doesn't actually depend in the following way. So inside the Picard group of Y, let's take the subgroup. I'll call it D. It's just, here's the picture. I've got a bunch of boundary divisors, these components of D. I just take the subgroup of the Picard group generated by the classes of the boundary divisors. Okay, and call that TD. TD subset of T pic Y. So this is just this is a toric variety. So this torus acts here. The torus, of course, acts on the base. It acts on itself. It acts on the base. The torus doesn't act in general on the family. If it does, it means the family is trivial. It means all the fibers are the same. But this guy does. So the conjecture is that TD, this acts equivariantly on the family, on pi. It already acts on R. So in other words, on A. It already acts on R in such a way that all the theta functions are eigenfunctions. All the theta I are eigenfunctions. And we can say exactly what the character is, are eigenfunctions. And then if I then I can mod out by this. And what will I get? So then I can take now I can take the quotient. So the torus of course acts freely on itself, and I have a subgroup of the torus. So when I act by this subgroup, it's a free action. So there's nothing scary about taking the quotient. So I take the quotient. So I'll go quotient. Quotient gives me, let's say, v mod TD going down to, well, T pick Y mod TD, that's T pick U. And now the conjecture is this is completely canonical. This depends only on U. This depends only on U. And this is the universal deformation of one of its fibers, V. This is supposed to be homological mirror symmetry mirror to the original U, to U. Now, one thing we do lose when we go to here, we lose a slight thing. We had absolute before we took this quotient, we had these theta functions on the nose. But the theta functions are only eigenfunctions for the thing I mod out by. So if you think about what that means, it means here I do have a basis of functions on each fiber, but they're only defined, without doing a little bit more thinking, up to individual scaling. So here I only have theta functions up to scaling. Theta functions up to scaling. Yeah. And I have to say this is an aspect of the theory that I don't fully understand. Exactly, what is the scaling exactly? Because in many, many cases, I'm sure there is no scaling at all. Like in the listed canonical basis, there's no scaling. And when we produce functions on a semi-simple group, there's no scaling involved. We just get them. But sometimes there is scaling. I don't fully understand the scaling. Okay, let's see. That's good. So that's enough of the conjecture to have things to say about, to talk about. What are the theorems? So the theorem is that it's true in dimension 2. Oh, sorry. Let me say a little bit more. At least push it a little bit. Sorry about this. The last point here, I don't forget when I wasn't numbering them. Let's say 4. Let's take V to be a fiber of this family that we produce. It's an affine log Calabi Yau of the same dimension as U. So it's every bit as good as U, and it's actually better because it comes with a basis of theta functions. So I can start with V and run the program again. So now just do it again, but start with V. So let's call V U check. So then the theorem, the conjecture is that U check check, so V check is U. So if I do it twice, I get the original thing back. Why is that even worth doing? I mean, I started with the original thing. But that has the corollary that says that U itself has canonical theta functions. Let's say OU itself has a canonical basis, well, up to the scaling issue, basis of theta functions. And more than that, I mean, it has all, more than that, it's the structure constants are given by counting rational curves on the mirror. So I completely recover U by this formula. So the point is, this thing says this is, this applies to everybody. So we get everybody this way. Okay, so the theorem is true in dimension 2. Theorem, this is Mark Gross, Paul Hacking, me, and Kinsevich in 14. It's true for cluster varieties of all dimensions. As I said in the first talk, a cluster variety means that it just means in this context a log Calabi Yau which has an open cover by algebraic tori. There are lots of such examples, but there's still measure 0 in the set of all examples. And then theorem, which I'll explain today, because it doesn't seem to fit this thing quite yet, with Siebert, is it's true for K3 surfaces. For K3 surfaces. So at the moment, I'm talking about affine varieties. How am I getting a theorem about K3 surfaces? Let me just explain. This is the application I want to talk about. Okay, so yeah, let me explain this. It's a fun thing. Yeah.
Is it obvious that this choice of fiber doesn't ruin the canon, like completely canonical?
That was what yeah, no, in fact, it's just the opposite. It's clear that it does not, that it does exactly what you're worried about. That was what I was saying, that before I take the quotient, I have a basis of functions on each fiber, and the torus that I act doesn't preserve those functions, it scales them. So that means, what that means in your thing is that, in fact, I have a basis of, on the fiber, but I really only know it up to individual scaling of each of the elements. So I don't screw up, I don't screw up, for example, the zero divisors of this basis, but I only really know them sort of up to scaling. Just as I did the example I gave at the very beginning. If I was over the integers, I would sort of know them up to plus or minus 1. Okay. So let me say, let's go back to the theorem here, and let's look at a, so what are we really saying here? Basically, we say you take a Calabi Yau. Let's say you compactify it to get one version of this. You get an algebra, or you don't compactify it. You get this algebra whose basis are all these boundary divisors at infinity. It has a multiplication rule on it, and when you take the corresponding algebra, you get this family, which is the mirror family. In this here, I assumed here for convenience that D supported an ample. For example, that said that U is affine. That made sense if I was interested in functions on U. But for the construction, we don't need this. We don't need this. And in fact, in none of the papers do we assume it. I just put it in for the thing. We don't need this. But then what happens is the multiplication rule is only formal. Here I can still tell you with exactly the same formula how to multiply theta 1 times theta 2, but you'll get an infinite sum. So what you get is you get the same family spec. This spec A, let's say sort of with a hat, over the toric variety for the Neff cone of Y with a hat. You only get the family in general over the formal neighborhood of the boundary of this toric variety. And in fact, there's people who know a little bit of Mori theory. So this is what's going on here. We started with the torus for the Picard group of Y. That's just some C star. We compactify it to some toric variety. What is that? Well, you can think of that as just sort of an AM. If it's it's just some slight generalization of AM. You have C star to the M. Partially compactified to whatever toric variety. And in fact, there's something better that you can take. A bigger toric variety, the toric variety for what's called the Mori fan of Y. That's more like a union of a bunch of AMs. That's closer to, well, something closer to PM. It's still not complete, but you just add in some more strata. So you make just a bigger toric variety. This is an affine toric variety. This is not usually. So the family extends to this by the same construction up to here. So in general, what we'll get is just a formal family with theta functions, but it only makes sense. It doesn't make sense over the torus. It only makes sense initially just at the zero stratum. Maybe here's a picture of, let's say the torus is C star squared sitting in A2. Originally, it only makes sense in a little formal neighborhood here, but we show that it extends along various parts of the boundary. So we have a family along the boundary of the toric variety. That's with the same features. So that's the first remark. That's actually how we do all the stuff. Is working near this boundary. And then secondly, let me just show you that here I've always been talking about affine Calabi Yaus. In fact, exactly the same philosophy and exactly the same construction applies to compact Calabi Yaus. So let's suppose, and this was actually the initial interest. Our initial interest was the following. So suppose I have, instead of my y, I have script y over delta. That's just my name for a disk, unit disk. Suppose I have a little one parameter maximal degeneration of now compact Calabi Yaus in the usual sense. Compact Calabi Yaus. So, so what is maximal degeneration? What does that mean? That means if I let D be this central fiber, pi inverse of 0, that this is now simple normal crossing divisor on Y. Let's say this is smooth. This is simple normal crossings. And what is maximal thing? It means it's dual complex. Let's say the dual fan that I just defined exactly the same way as before. The dual fan is has maximal dimension. It has dimension dim y. That's what maximal degeneration means. So this is what you sort of a more traditional thing in mirror symmetry. So I have this maximal, so smooth general fiber degenerating to a maximal degeneration. For example, in what are such things? In dimension, for example, in relative dimension 1, I would have, say, an elliptic curve. Most normal people, I think, would draw that like this. Degenerating to the central fiber would be, that's why I don't draw it like this. It would be a wheel of P1s. Or you could just draw one node like this, so a cycle of spheres. That's what a maximal degeneration looks like in.
I think you should assume the essential skeleton has maximal dimension, not the dual.
Well, if I make it simple normal crossings, I'm okay.
Because you should take a minimal model. If it's not minimal.
Oh yeah. Oh, sorry. I didn't say. Sorry, man. I should have said k. I didn't. Thank you. I want k here. I want ky to be trivial. This is Calabi Yau. So the canonical class is the family of k-trivial varieties. Yeah. So then it's just like. So maybe I should stress this. Yeah. Sorry about this. This pair. I'm just suddenly wheeling this out. But note, now this pair, yd. This is just like the things I've been talking about. A slight, and then u is y minus d. This thing has a volume. In this situation, this has a volume form. This again has a volume form with simple poles. Only simple poles. It's doesn't quite. It's not log Calabi Yau because this is not an affine variety, but it's a very close analog. Same philosophy applies. There will be algebraic situations where this is, say, A1, and this is just absolutely exactly the kind of thing I've been talking about. But is everyone getting it? So if you have a degeneration of Calabi Yaus, you look at the central fiber, that's like this boundary D I've been talking about. If I throw that away near the central fiber, that's like this U I've been talking about. And all the same algebra, everything, exact same definition works. The same dual complex, everything. This is one example of such a degeneration in dimension 2. I could have, for example, K3 or a abelian surface degenerating to, well, I call it a soccer ball. What does it look like? It looks like, well, it doesn't quite look like this, but let's say the thing people usually draw is something like a bunch of P2s, something like x, y, z, w equals 0 inside of CP3 with those coordinates. But that's not quite right. That's not the total space is not smooth. So this would be a bunch of P2s glued together. You get a bunch of blown up P2s. You'll have to blow up these P2s. So you get some blown up P2s. But what it looks like is the pieces. What are the pieces here? The pieces here are a bunch of P1s with 2 points glued together. These are like little yi di's. These are the dimension 1 versions of the things I've been talking about. Here, what you have is the pieces are things like this. These are the same yi di's. Now the dimension 2 version. The things I've been talking about in the 2 lectures. Glue them together exactly the way the panels in the picture, exactly like the panels of the soccer ball glue together. Okay, people get roughly the idea of how this thing works. So so that's a maximal degeneration, and that's just the total space of this, or total space, say, with the central fiber removed, behaves just like the U I've been talking about. But it has a special feature, this algebra. Let me mention it. Let me just mention a feature of the algebra in general. So, when I have U, suppose I've got a rational function. Let's make it a dashed line to A1, some rational function. So what I want to say is that in the compact case, I'm going to get this algebra, but this algebra is going to be naturally graded. And I can take proj of it, and then I'll get a family of projective varieties. Let me just explain. That just falls out of the formalism. So in general, let's suppose I have a rational function on my U. Then, of course, I get a map from the tropical set, or I get a natural map from the tropical set to R for example, what does u trop do to these integer points? You know, some divisor e with m, or some valuation v. This was the valuation. What does it do? Sorry, it sends. What's the map? I'm saying to z. What does it do? Well, what should f trop? So this was z. I was taking an element of it. What's f trop do to some pair of a boundary divisor with some multiplicity? What should it be? It's the order of pole of f along that divisor. So that's the order pole along e of f multiplied by m. So that's you get this natural function. And if f is regular, these are linear. Min-convex. So what do I mean by min-convex? What I mean is this is supposed to be, you know, locally the minimum of linear functions. Linear functions. It's a piecewise linear function which is min-convex. But I was stressing that it doesn't make sense in this context to talk about linear. So, for example, if you choose any torus, if you give it any linear structure given by any torus, this will be simultaneously min-convex in all those structures. Or there's other ways of getting a linear structure. In fact, what's really true is you can just use this to give yourself a notion of what you can do some convex geometry now by calling these the convex functions. That's a kind of a cool thing to do. Anyway, you get such a thing, and maybe more just you get that. But also, what it does is, let's draw a picture here of what's going on. We've got the tropical set, which roughly looks like a lattice inside of a vector space. And if I look at this f trop inverse of some number, that'll be a sort of polytope in here, maybe bounded, maybe not. Let's say where it's bigger than or equal to, let's say f trop, let's look at the set of x such that f trop of x is bigger than or equal to some number. That will be a polytope. I'll draw it as bounded here. It may or may not be bounded. That's my version of a convex polytope. Convex polytope. Polytope. Inside, this is the basis of my ring. This should remind you of the toric case. And this, in general, what this does is this gives a grading. This gives a grading, a filtration. Filtration. It makes it a filtered ring. So A becomes a filtered ring. We're just AK is just this set. It has basis the set of thetas where where f trop of p is bigger than or equal to minus k. You just have to check that you have to check from the definition that AK AJ is AK plus J. That will be immediate from that's quite easy from our structure constants. Even better, if f is invertible, doesn't have any zeros on U, then I also get a grading from, I can also take the inverse of f, and then it implies that A is actually graded. It's a graded ring. Graded ring, and I can take proj. Just like you would in the toric case. So that's what I'll do. So the application that I'm looking at the moment is this. So what was the application here? We started with a maximal degeneration of, this maximal degeneration. I'm taking the case where U now is y minus the central fiber. It's pi inverse 0. That just comes with a map down to delta star. And so now the algebra A is graded. Because this guy is mapping to, this function is nowhere 0. This is my f. A is graded, and I can take, and then we'll call, let's say x01. Let's call that x01. That's the proj of A. That now has a map to the toric variety for the Morifan of y, just living along the formal boundary of this toric variety. So this procedure produces this big family of now compact Calabi Yaus over the boundary of the toric variety. Okay, so basically the same definition as before. And now let me tell you, and now, oh, there it is. This turns out to be a cool thing. So let me state the theorem here. So what do we get? So let me talk about moduli of K3 surfaces. So a little application to moduli of K3 surfaces. So let's let Fg be the set of pairs x01, where x is a smooth projective K3 surface, smooth projective K3, and this is an ample line bundle on it, and O1 is ample, it's positive, and its first Chern class is 2g minus 2. If you have something on a K3 surface and you square it, you get an even number. So you can write this. Why the g? What that means is that if you take an element of the linear system, that's a genus G curve. Well, that's a nice fact that comes from the that's true about K3s. It's a genus G curve. Yeah, so this is a nice moduli space, and its mirror, in the sense of say Dolgachev. Lev Borisov gave a couple talks about this kind of lattice polarized mirror symmetry. The mirror to this is if you consider, so these guys, this is a big family. This is a 19-dimensional family. The typical element here in this family has only one line bundle, just the line bundle you say it has. The mirror to this, our guy is actually a one-dimensional family. Those are guys which have their Picard group. The biggest the Picard group could be is rank 20. To get dimensional, you take things like 19. So the mirror are, if you consider K3 surfaces with pick of rank 19, then this has countably many components. They're countably many. They're just in bijection with the numbers g. They're just in bijection, just determined by a single integer, the bijection with g. So, so Fg, there'll be a certain mirror family. Let's call it y over delta. It depends on g. Y, I should put a g here. Depends on delta. What is it? There's no mystery about it is. This is a moduli space of K3s. I tell you in this theory what you tell is not just that the rank of the Picard group is the Picard group has a certain rank. You say that a specific lattice lives inside the Picard group. So here there'll be a specific lattice of rank 19 that you build up out of the data of this. It's not important for what our thing is. Just the important point is for each Fg there's some one parameter maximal degeneration that people already knew about, that they kind of knew had something to do with mirror symmetry, that had some mirror properties. So for us, we just looked at this. So this is a maximal degeneration. Maximal degeneration. One parameter maximal degeneration. So we can stick it into our machine. And I would say, really, this is about as much as we knew about, at least me, about K3 surfaces, was that this was a family of K3 surfaces. So stick it in the machine, and what do you get? So the theorem is, is that there exists a canonical toroidal compactification Fg inside of Fg bar. Forget that it's toroidal. There's a canonical way to compactify the moduli space. This is a space. A nice thing. It's a bounded symmetric domain or a symmetric space. There was a theory developed by Mumford for how to compactify things. He wanted to compactify Ag. Unfortunately, it involved putting a certain cone structure on a fan structure on a certain round cone, and when you look at it, it looks like there's infinitely many equally good compactifications. We realized that this Mori fan was the right thing to use. So the point was this is not so deep to figure out what's the right compactification to choose. I mean, to produce a compactification, Mumford produced infinitely many. So we picked it. But the cool thing is, so there exists a canonical toroidal compactification and an extension, this is the thing that really matters, of the universal family into here. So we compactify the moduli space and the family extends. And I'll make a statement that is not factually correct, but it's actually, the thing we prove is much cooler than what I'll say. But to explain what I said, it will just be a little bit too detailed. What I want to say is that, so it's a toroidal compactification. That means the boundary really does look like the boundary of a toric variety. So I want to say that the formal neighborhood of the boundary, so you had this moduli space, you add on some boundary, and now you look at a little analytic neighborhood of the boundary. Inside of here, so inside of FG bar, the boundary is the toric variety. It's actually this. It's something close to this modulo a discrete group. Toric variety of the Morifan of Y hat, and our family restricts to the thing I wrote down before, this proj A. This was our proj A. So what we're saying is we find an extension, we compactify the moduli space and show that our family that we built just by writing down proj of this algebra just glues right on there and fills up, completes the moduli, completes the family. So what do we get out of this? So a corollary of this is a theorem. This was a conjecture of Turin. So this is Turin's conjecture. Turin's conjecture is that if I have that K3 surfaces have an analog of theta functions, so that if let's say x01 is a polarized K3 surface over power series field over CT, which is the maximal degeneration when thought of as a one-parameter family, maximal degeneration, then it has theta functions. Then it has theta functions. An analog of the that's exactly this. This is, for example, a canonical basis of the coordinate ring of all powers of the thing, XOM. If we were talking about abelian varieties, these theta functions that we reproduce the classical theta functions for abelian varieties. So Turin had a reason, based on mirror symmetry, to think that they should exist for K3 surfaces. So we do much more than this. We produce this is a single K3 surface. This is the universal K3 surface. So we are really giving you, what are we really doing? I'm giving you a basis. I give you a basis for the homogeneous coordinate ring. That means I give you the universal K3 surface living in a projective space with canonical coordinates, and I give you the multiplication rule. So I also give you the equations of the K3 surface. So this procedure produces all K3s and the equations of all K3s. And really, this is all without thinking about K3s. Without thinking about K3s. Just like on the first day, that's what I really like about it. We got this basis of representations of semisimple groups without thinking about semisimple groups at all. And it actually was a nice surprise in this procedure that I think people who studied K3s, really, hopefully it's surprising to them. It's very surprising to me. So you can ask, all right, so I had all these K3s. I compactified the moduli space. Now I've got a bunch of singular K3s on the boundary. You can say, what are these singular K3s? So which sort of degenerate K3s occur? Well, in the 80s, starting in the 80s, maybe it was the 80s and much into the 90s, there was a lot of study. People studied degenerations of K3s. And there's a really nice classification due to Kulikov classification. He has these type 2 and 3 degenerations of K3s. For example, this family y over delta, this mirror family y over delta, that's an example of a type 3 degeneration. They're really beautiful things. I think most people expected to see these things in the boundary of the moduli space. None of these occur. So there are nothing from Kulikov appears in the compactification. It's really kind of amazing. Compactification. So the one bad thing about the Kulikov compactification, so what is a Kulikov thing? He started with a K3 surface over power series, and he wanted to complete it in a nice way. Some version of stable curves, sort of, for K3s. He found this beautiful theory, but unfortunately the central fiber was not unique. There were infinitely many different things you could stick in. Well, that sort of does tell you that if you produce a canonical compactification, it's not going to be there, because there's got to be a unique limit, as I probably won't have time to explain. So these do not occur. Instead, what occurs are something much simpler. Let me tell you, this is almost everything in the boundary. So what occurs? this is almost, for a long time I hoped this was the only thing, but I don't think this is quite right. I wish this was the only thing, but this is quite close. So do the following. So pick G plus 1 points on S2. Well, maybe put it another way. Take a triangulation, form a combinatorial triangulation of, this is a triangle, it has nothing to do with delta from before. This just means triangle. Form a combinatorial triangulation of S2 with G plus 1 vertices. For example, when G is 3, so just take a sphere, G plus 1 points, divided into triangles. Then associated to that, there's an absolutely canonical K3 you can write down. So from this, I can define, let's call this thing B underscore. B is what our name for the tropical set. That's the sphere in this case, and we have this B underscore. Means you decompose B. Let's call it, we have a sort of X B underscore lives canonically in a projective space PG, where this just has coordinates. This is just a projective space with coordinates, one for each vertex. And what is this? It's just a union. This is just a union of coordinate P2s. Maybe you see just how you would define it. Each vertex gives you a coordinate. So given this triangle, I look in this projective space at the points where all the coordinates except for these 3 are 0. I just get a linear P2. They fit together exactly like the triangles. They fit together just like the triangles. And what's the O1? And the O1 restricted to each component is just linear. So I think it's kind of obvious that this is the most degenerate possible thing you can get for a polarized surface. You've got P2 with a line on it. You can't degenerate that. And this is almost, these appear all over the place in the boundary. And what occurs on our boundary, so over the type 0 cusp, that's where most of the boundary goes. For people who know about, that's where all the action is. There's type 2 and type 3 degenerations. So this is really, instead of, let's put it this way, instead of Kulikov type 3, we get, instead of his limits, we get this thing, or what you get if you smooth some of these double curves. So what I mean is this can smooth a bit, this could smooth out. And what you get is, instead of a bunch of P2s, you get a bunch of toric surfaces, no moduli, a bunch of toric surfaces stuck together. So there's just finitely many combinatorial structures, just the dumbest things stuck together. So that's everything on the boundary of the thing. Okay. And so maybe let me just finish by explaining. You could ask. So let me say a little bit. This actually why I got into the subject was because I wanted to compactify moduli of K3s. Let me tell you what I think is like a really cool problem, and why it led to this stuff. So even if you just even if you aren't following anything, you could just start again right here. I'll just start with a cool problem. So let's let M be moduli. Let's consider the set of, let's say, MK trivial. This is the set of pairs XO1, where X is a Calabi Yau, just means a K trivial smooth projective variety, and O1 is a positive line bundle on it. This is a nice thing. So a theorem of Matsusaka and Mumford, and then Bogomolov, Tian, Todorov, is that this is a smooth and separated space. So this is smooth and separated in Hausdorff. So this is a nice thing. So moduli of Calabi Yaus is nice. Most moduli spaces are not nice, but this is nice. So what's a natural question? So I think the really cool question is, find a nice compactification. So this guy's smooth, so you can hope that this guy is close to smooth. Ideally, maybe smooth with normal crossing boundary. This guy has, of course, a nice family. You would like this to have a nice family. An analog of MG, a version of mg n, say, in mgn bar. That's everybody's kind of idyllic example. By comparison, so what's kind of surprising to me when I first realized that this thing was smooth, there's almost nothing was done on this, even though this is such an attractive looking problem. By comparison, people studied moduli of positive varieties, varieties where the canonical class is positive. Here, just about the entire moduli space and its compactification, there's a modular compactification due to, mostly, I think due to, the original ideas are due to Mori, Kolar, Shepard-Barron, and then the really serious, some hardcore stuff you need to do it is due to Haken and McKernan. This is one of the triumphs of Mori theory, is to be able to construct this. So you construct k0 inside of mk greater than 0, and I think I'll even have time, maybe not. This is what are called stable compactification. There is something called this just direct generalization of this. But I don't think anybody would say that this is a nice compactification, because this space itself is universally singular. There's a theorem of Munyev. Just every equation you can write down, any system of equations you can write down, every singularity that you can write down occurs in the interior of this space. So the space is as nasty as you could ever ask for. So this is certainly not a nice compactification. I think this is a way more attractive problem. So why did nobody ever consider it? Or why was there never any progress on it? Because what do you have to do to address this problem? What's the very first thing you have to do? What does it mean to compactify the moduli space? Well, what it really means is, in a canonical way, what it really means, you have to address the following problem. So I start with x01 over a punctured disk. That means punctured disk now. And the question is, that means I have a punctured disk mapping into this moduli space, which is sitting in M bar. So here's my little disk. I'm going to the boundary. If there's a moduli space, if it's compact, there'll be a limit here. And if it's Hausdorff, there's only one limit. So that means that if you have to ask yourself, what central fiber to fill in? What is the canonical way to fill in the central fiber? And this problem is really hard, I think, even for I don't think this problem was solved even for genus 1 curves. There is a compactification of moduli of genus 1 curves, but if you look at it and ask yourself, what's the limit? I don't think you'll be able to figure it out by looking at the definition of the thing. Maybe better to ask a number theorist. But so what I mean is, here's what I mean. Let's take a degenerating family of elliptic curves. Let's say we have a bunch of elliptic curves, and the central fiber looks like, let's say, a triangle. So smooth elliptic curve degenerating to a triangle. So this x now is a surface. Let's say we're over A1. This is a surface. The general fiber is elliptic curve. The special fiber is this triangle. You can blow down in the total space. You can contract any one of these components or any pair of components. So you might say, this is pretty nice. That's semi-stable. But I can blow down one of the components, and I'll get something like this. I can do that in 3 different ways. That's just as good. And I could also go to this in 3 different ways. They're all just as good. And the polarization doesn't help at all. So which one is the right one? Which one is right? Well, OK, by contrast, what can you do by contrast, how about if k is positive? If k is, the problem here is that k is trivial. When k is positive, people know what to do. So what do you do? There, what you have a notion of stable. Stable means 2 things. It means that kx is positive. And the second thing is a singularity condition. Singularity condition. I don't have time to, I won't tell you what the singularity condition is just because I can't. The really important thing about the singularity condition, people always write down by describing how many automorphisms the thing has. That's not what is important about it at all. What's important about it at all is that the singularities are such that if you have 2 birational ones, they have exactly the same sections of k. And that's what implies that there's a unique way to fill in the central fiber. So the important thing is here you get a unique central fiber. Unique central fiber. It's because of the birational invariance of the sections. You get a unique central fiber. This also works. This is just what MG, for stable curves you probably know. This also works for pairs. So there, what do you have? You have a variety x together with a combination of divisors, where it looks going to look weird. You're allowed to take these things rational numbers. So positive rational numbers. So these are divisors on x, effective divisors, with some rational numbers in front. Then there's a notion of a stable pair. But for example, if the AIs are all equal to 1 and we're in dimension 1, these are just, this is the usual MGN bar, just stable pointed curves that you've seen. That generalizes nicely to higher dimensions with the same properties. You get a good moduli space. Okay. Now that's looking good a little bit. So yeah, what's stable mean in this world? Just to say, this means that kx plus gamma is that sum. That this is positive, and then there's the stable condition. There's the singularity condition. But now suppose, without knowing much about this, here's what you can observe. Suppose that kx itself, let's say x is smooth, and that kx is trivial, and d in x is any positive divisor, is any ample. Then I can look at kx plus epsilon d. That will certainly be positive because this is 0. So that will always be positive. This guy's 0. Epsilon's positive. And when epsilon is sufficiently small, the singularity condition is an open condition. X is smooth, so it's got good singularities. This will have good singularities if epsilon is small enough. So this will satisfy the singularities, satisfy the sings. So what I'm saying is, if we studied instead moduli of pairs x and d, where kx was trivial and d was positive, this would just sit inside the moduli space of stable pairs. And I could compactify it by taking the closure, because this is compact. See what I'm saying? So if instead of having a line bundle I had a divisor, I would know what to do. I would just take a small coefficient and take the stable limit. So our idea, this was my idea with Paul Hacking about a little more than 10 years ago, was that mirror symmetry suggests, so here's the moduli space. Here I've got that problem. I've got my little disk, and I want to know what limit to take. I've got my little family. What's the picture looks like this? Then I don't care, because Mumford says there's a unique limit. I'm only worried when I get close to the boundary. So I'm getting close to the moduli space. I've got this, xt01t. I've got this family of polarized varieties. When I'm near the boundary, a polarized variety should come with a basis of sections. So here, h0, xt01t, this should have a basis. So I don't just have a line bundle. I actually have loads of sections. And I can take, let's say, theta1 up to theta g, and I could define a divisor, theta, as, say, the 0 locus of theta1 plus theta g. So, do you see what I'm saying? The conjecture says that there's a canonical basis of sections. So when you get close to the boundary, you have loads of divisors. You can do whatever you want. You've got the whole basis. So, for example, you're living canonically in projective space. You just slice it with a fixed hyperplane. That's all we're doing. Everybody lives in the same projective space canonically. We just slice. And now, x, I can take my x here together with this tiny secret. So what I say is it's secretly a stable pair. Secretly a stable pair. So what limit should I take? When I get close to the boundary, suddenly I have these magical theta functions. So I have this divisor. I just take the stable limit. And what we show is that is the limit that we get in our family. Let me mention that this idea, you can use this idea for abelian varieties. It's new even for abelian varieties. You don't need to prove that there's a basis, because there's this theta function basis. My student, now graduated student a couple of years ago, Yuesheng Zhu, who's at Penn, he applied this philosophy to get a nice compactification of moduli of polarized abelian varieties. He got a nice space. It turned out it was equal to a compactification that was already known to Olson and Alexeyev, but he gave, he showed that their compactification. He explained what's the limits in there. Okay, but anyway, so this is why I got into mirror symmetry, was in order to compactify the moduli space by, so if this says, okay, that's what the limits should be. But of course, to do it, you got to prove that this has this basis. All right.
Can you say what that basis does in your genus 1 example?
Yeah, this is the, now, these are the, I'm not super good at what the, so if you have a degeneration of so there's a theory of theta functions for elliptic curves. So you're basically asking me, what is a theta function for elliptic curves? That's what. So let's say, first of all, let's say I have a principally polarized abelian variety.
And how does the theta function tell me which of these blowdowns of your triangle?
Oh, sorry. That's what you're really asking. That's really the same as. So I just said if you have points instead of if you have points instead of if you have curve with points on it, you know what the limit is. It's the stable limit. You know what stable curves look, stable pointed curves. That's the limit. So for example, if you're in this situation, you have one point. You had a family with a section. That's the guy that's going to live. If their points are distributed, they'll tell you how to do it. Then maybe that's what your question is. Yeah.
Is one of those points called 0 or 1 or something?
Well, no, this will be, so in general, what I'll do, if it depends, let's say I have an elliptic curve with O1 of higher degree. If it's degree 1, I'll just get 1 point. That's what the theta function is. If it's higher degree, there's then still, it's not obvious that if you have an elliptic curve and I give you a line bundle, that in fact it has a basis. In fact, it depends on choosing some discrete data, but that data is the same as being close to the boundary of the moduli space. So you'll get a basis of sections and you'll get some bunch of points, they're related to, they're related to d torsion points on the elliptic curve. It's not what they are, but they're related to that. And then, so your general elliptic curve has points on it. They all have points. And when you have points, then you can take the stable, then you're in the world of MGN bar.
It will be just blowing down all the components that don't have.
Exactly. Sorry, I'm just being stupid. You have kx plus, you want to make, as Tony said, what you want in the end, what does it mean to be stable? You want kx plus delta to be relatively ample. Here kx is trivial, so you want your divisor to be relatively ample. If it's 0 someplace, you crush the thing where it's 0. That's a much better answer.